My name is Marko Vossi. I'm a business development director of our family business called Vossi Group Oy. And we are as a reseller of SLM Solutions metal 3D printers in Finland and also Baltic states. And now I would like to say a few words in Finnish about our position and the possibilities maybe for you too. So, elikkä tosiaan niin toimitaan Vossi Group Oyn, eli perheyrityksemme toimii SLM Solutions metallien 3D-tulostimien jälleenmyyjänä Suomessa ja Baltiassa. Ja meillä oli tuossa alihankintamessulla ensimmäinen tämmöinen niin kuin launch-tilaisuus 280-mallin 3D-tulostimella, mikä on tämmöinen meidän näkökulmasta alihankkijalle hyvin soveltuva tulostin, eli siinä pystyy materiaalin vaihtamaan toista materiaalista toiseen noin 1–2 tunnin sisällä, eli se on hyvin joustava, eli tämä teknologia on mennyt tässä eteenpäin ja siihen saadaan kaksi laseria sulattamaan materiaalia, ja sitten SLM:ltä löytyy myös tämmöinen markkinoinen oikeasti ainoa meidän näkökulmasta ainakin niin tämmöinen sarjavalmistus tulostin, eli 500-sarjainen, jossa 4 laseria pystyy työstämään samaa aluetta. Mutta Hendrik kertoo näistä kohta vähän enemmän. Nopeasti meidän yrityksestä, eli ollaan toimittu pitkään tuolla konepajateollisuudessa ja sinne erinäköisiä tuotantoteknologioita toimiteltu, ja tällä hetkellä 6 paikkakunnalta Suomessa toimitaan, ja sitten meillä on tuolla Virossa tytäryhtiö ja Taiwanissa maatoimisto. Ja tosiaan 20 henkeä on, josta puolet on huoltotoiminnoissa ja puolet myynnissä. Tuossa on vähän muita teknologioita, eli nämä kaikki muut kai nyt sitten tässä seminaarissa lasketaan, että nämä on niitä perinteisiä. Mutta tosiaan niin toi 3D-tulostus on nyt sitten meillä niin iso asia ja halutaan olla siinä vahvasti mukana. Siinä on joitain meidän asiakkaita, kenen kanssa touhutaan, mutta ihan sanotaan yhden miehen yrityksistä niin sitten isoihin organisaatioihin. Ja tämä on oikeastaan nyt tämä, mitä me nähdään, että meidän rooli on tässä liittyen 3D-tulostukseen, niin halutaan olla tämmöinen teknologian haltuunottokumppani, eli yhdessä meidän asiakkaiden kanssa käydä läpi, että mitkä ne teknologian mahdollisuudet on ja miten ne muutetaan teille kilpailukyvyksi, ja toisaalta sitten se, että miten me saadaan teille vakaa prosessi, eli suuri käytettävyys, ja pystytään sitten sitä optimoimaan sitä tuotantoa, ja sitten kehitetään jatkuvasti sekä teidän tuotteita että tätä tuotantoprosessia. Ja jos tässä on niin kuin joku itselle tullut selväksi, kun tämän aiheen kanssa on tässä jonkun aikaa nyt touhunnut, niin perinteisin valmistusmenetelmin valmistettuja kappaleita ei yleensä kannata 3D-tulostaa, vaan se, että ne suunnitellaan ihan puhtaalta pöydältä täysin uusiksi ja pyritään tämmöisiin täydellisiin tuotteisiin, mikä on nyt ensimmäistä kertaa mahdollisia, ja saataisiin tämä fokus tämmöisiin uuden sukupolven tuotteisiin, eikä niin kuin omasta mielestäni se on monesti meillä täällä Suomessa, niin on sitä, että miten me saadaan koko ajan vaan senttejä pois niistä tuotteista, ja ei ehkä käytetä sitä aivokapasiteettia siihen, että miten voitaisiin tehdä jotain täysin uutta, ja mun mielestä tässä on semmoinen teknologia, mikä mahdollistaa sen. Mutta ei se enempää oikeastaan Vossista. Nyt mä päästän Henrikin. So Henrik, now this brief introduction and you can continue.
So I will continue in English. Pekka, thank you very much for the introduction and for the opportunity that I can give a short presentation of SLM Solutions today. Actually it's a pleasure. I think I was already several times in Finland now since I'm working for SLM Solutions starting on beginning of 2014. I started my business here for Northern Europe with SLM. And I would like to, of course, introduce the company, but I would like to focus more on a case study for aerospace industry, or aircraft industry. So we talk today about new perspective for high productive batch production. That means we are already one step ahead from prototyping, and we are really at the inflection point of serial production. Actually, you already gave some information about me, and so I just would like to continue.
The process of making a part out one day at a time instead of machined away material. It's a radically new way of making things. You can almost change the design on a whim. How does additive manufacturing change the way products are made? I'd say take a look at the example of this bracket right here. This is how you make it conventionally with very little geometric complexity. But with additive manufacturing, complexity comes for free. Therefore, I can make the part that is functionally equivalent, but is a lot lighter. Additive is just a great game changer for GE. We can iterate a lot faster, get designs through testing a lot faster, and we can make shapes and designs that were just not possible before. In fact, over the last 10 years, GE has made tremendous strides in additive manufacturing, and we are now taking it into production. We will be in production in the next year and a half to 2 years in anticipation of the launch of the CFM LEAP engine. The technology is here. We've shown that it's viable. We've taken it out of the lab. It's almost ready for industrial use. We just need the infrastructure to come together so we can take it to the next step. This truly is the future of manufacturing, we believe. It's going to find a really unique niche in manufacturing technologies. It's not going to displace conventional manufacturing, but it's really going to be a game changer when it comes to making complex shapes with high performance, which is so critical to GE.
Okay, this was the lucky punch, hopefully to wake you up this morning, because I recognize that you have very nice, comfortable chairs here in the university. This is not usually in Germany. Usually you have wooden chairs because the people are afraid that the students can fall asleep. So hopefully now you are fully awake for listening to the next 1.5 hours to my theoretical explanations of SLM Solution Technology. No, sorry. So I just want to give you a brief introduction, and I would like to start with a short agenda, so what you can expect this morning from me. On the one hand, of course, a short introduction of SLM Solutions Group. Then I will show you a little bit about the initial situation of part production. And then I will show you the idea of high batch repair by means of SLM Solutions, and of course, at least how we think to increase manufacturing productivity. And this is not only, let's say, a vision, it's already available. Okay, SLM Solutions is manufacturer for selective laser melting systems, and we are located in Germany, very far in the north of Germany, very close to the East Sea. The city we are located is Lübeck. So usually we work where other people spend their vacations. We have a long-term history in rapid prototyping. I don't want to bore you with a long history of different joint ventures, and sometimes we changed also our name, the company name. But we started already with rapid prototyping, that means vacuum casting, metal casting in the 70s. And at the early stages of this technology, when this technology was invented, we already started at the late 90s, starting of 2000, with developing and selling selective laser melting systems. At that stage, more or less, to universities. The technology was really not mature for the industry. You had very porous parts. But over the years, we developed and made very good improvement, so that our goal for the future was to have one day machines which has an industrial standard for industrial serial production. And we reached that goal in 2013 with our SLM 500, working with 4 times 400 watt multiple laser systems to increase productivity and increase the build speed 4 times in comparison to the, at this stage, in the market available machine systems. In summary, we have 3 machine sizes available: the SLM 125 with the smallest build envelope, and then the SLM 280, the middle-sized version, which is more or less the most wanted system in the industry at the moment, because it's a very good system to start with the technology. It has already a size of 280 by 280 in the flat surface in millimeter and 350 in the Z-axis, so that you can already produce a lot of industrial applications with this machine, but it's also flexible in changing materials in a short time. And then, of course, our flagship, the SLM 500, which is really dedicated to serial production in one material. We cover a lot of relevant markets already, and you see some facts and figures over here. So aerospace is, of course, one of the most important applications for us, and we have a huge customer base already in this area. For example, GE, the guy from the video you have seen before, Prabhat Singh, and GE is, I think, one of the early starters with this technology, and they made a really good approach in the past, and they're operating our systems already also in the production area. So then we have a lot of service centers already producing several parts for several industries. If you take together healthcare and dental, then to the medical area, then you can say medical industry is also a huge part of that. Academic institutions, so that means universities, research centers, I think more than 70 or 80 of them all over the world having our systems already. And automotive is an increasing industry for this technology. We are not talking about serial production in that applications, but of course about a lot of race cars and customized cars. So this is a growing area, and there is a lot of other industries already looking into this technology, and I believe that a lot of industries at the moment are not aware of what is possible with this technology. But I'm really glad about the presentations we had this morning, it gave you a really good overview, and that's the reason I don't have to give you 1.5 hours lecture about the theoretical things. It was really good, and I loved it because it gave you a really good overview. Okay, coming to this case study in the next slide. Of course, we have some initial situations regarding the conventional manufactured parts. We would like to change now to additive manufacturing. And usually, and these I think are usual questions everybody of you have, what about surface roughness? What about mechanical properties like strength and hardness? What about accuracy? What about density? What about stresses? Some of my previous presenters already gave you some information about that, but of course for this project we had some dedicated requirements for the parts which are conventionally manufactured. So there was the idea of what kind of surface roughness is needed for these parts, what kind of strength is needed, what kind of accuracy they require, and also the hardness and the density. And you see a density in that case was 99.x, so usually we can achieve densities by 99.7% or even higher. It's a little bit dedicated to the material. But in that case, it was not important to be 99.7. It could be even less, but it must be more than 99.0%. And of course, the question was, what about the influences of this layer-by-layer welding process? So that means we cause stresses in a part by layer welding. So since this is a laser welding process. And we also had to discuss about the physical system. Now you are asking, okay, this is a sales guy, he should have no bloody idea about physical systems. You are right, but anyway, I would like to try it. So just to be aware of that, very often when you think about laser cutting, then you know, okay, as more laser power you can use, as bigger plates you can cut or whatever. Or when you talk about cars, as more horsepower a car has, as faster it drives. That's fine, but it's completely different for additive manufacturing because we just talk about energy density. So when you process a material, you need a dedicated energy density for that material. And the equation of energy density is shown on that slide. It's laser power divided by build rate. And build rate, again, is a product of scan velocity, layer thickness, and hedge distance. So that means if you increase the laser power and you want to keep the energy density constant, then you also have to change these other three parameters. To increase scan speed is not an issue, it's easy. If you increase layer thickness, you reduce your surface resolution. That means That means the surface roughness is getting worse. And if you change the hedge distance, which is usually the distance between the different weld tracks you see over here, then this is usually not possible because your spot size of 82 microns is a stable value. So if you want to increase that, you have only one chance. You can only defocus the beam. And this is important when you increase the laser power. You have to defocus the beam up to 500 or 700 micrometers. But that would mean, at the end, the accuracy of the process is also worse again. Because it's interesting when you produce bulky parts with very solid areas, then it might be good to increase the productivity by defocusing the beam. But as we have seen this morning already, the benefit of additive manufacturing is to make topology optimization, to get lattice structures with thin wall thicknesses. So what the hell will help you with a defocused beam? Nothing. So you need this small beam size. And that's the reason you can only produce with 400 watt or less for the different materials. And that's the reason, and this is one of the reasons, just to give you that briefly, that we use multiple 400 watt laser systems in our machines instead of increasing just the laser power. But this is another story. I will come to that later. So just to give you a rough overview about the physical system behind of this technology, I think this is important to know, to understand one part of this selective laser melting. And then, of course, we talk about materials. So you see here, we had this discussion already this morning, a huge variety, I think already about different processable materials with this technology. In general, it was right, you can process all metal materials which are weldable under, this is important, room temperature. But not all materials are available in the market in a powder form, and not for all materials we have already a parameter setup. But what was already mentioned, that this changes possibly year by year. So it was the question, what kind of material? And of course the specification of a material is very important. We had that information already this morning. So spherical particles, that it is shown like here, the powder distribution size, a good flowability, dryness, and of course the chemical purity. So these are the, let's say, rough requirements for each customer project we're usually talking about when it comes to case studies or business cases. Coming now to this dedicated case study, then we are talking about a project with different work packages, and this is shown here on that slide. So we are talking about a work package, what we had to do with, of course, fixation and clamping devices. And we're talking about a repair project, so refurbishment of turbine parts. And of course, we're talking today about quality assurance, and in this case about skin and core strategy. So this is a rough overview about the project itself. The most important thing is that we are trying to repair, in this case study, parts from a turbine, and these parts are so-called shrouds. They are located in a turbine, and they are, after some working hours of that turbine, usually they have an area of wear. And today you just dismount these parts, throw them away, and put new ones inside. It is very expensive because the parts are very expensive, and the idea is just to remove this weared area and produce again with additive manufacturing this area with new material and refurbish the parts. So this is the rough case study, and I would like to make it more easier to understand. I would like to show you a movie of this still running project, I have to say. I hope it's loud enough, but it's just music, so I will give some explanations. So we are talking about future repair and, of course, high batch production. So what you see over here are these shrouds, and this area you also can see when it's focused again. This is this area of wear. So what we invented in the first step together with our customer was this clamping device, because what we need all shrouds in the same level. Because what we do when we mounted all the 42 shrouds into this clamping device is we mill them flat or down by 3 millimeters. And so that's important that all parts are in the same level. And of course today this is, as I said, it's still a running project. This is still made manually. The idea for the future is of course to automate that, to reduce the manual work. So now you will see a process which I believe everybody of you really knows quite well. So as I said, we will mill down now all these shrouds by 3 millimeters. And the material we process here is a special nickel-based alloy, which was not listed on that material list I've shown you in the previous slide. Sorry. Now we put this clamping device with the milled parts into our machine. You drive down the table in negative Z direction so that you get the first flat layer. Then we recoat the powder with this powder hopper. And in the next step, in this case it is an SLM 280 machine with twin laser, so 2 times 400 watt laser source. We produce the material again on that parts. And unfortunately this is not real time, not this year, possibly next year. Of course we are always working on higher build rates, but I think we are already up to the notch with these multiple laser systems. And so you see always how this process also works. So after that you can suck the powder directly out of the build chamber. It is sieved and directly provided for the next build job. And after sucking all the powder out of this build chamber, you take off the plate with the finished parts, and you dismount them again, and you blast them usually, and then you can see the difference from to the new produced and repaired surface. And this business case is at the moment really green, because it's cheaper to repair it instead to change it and to pay the price. What is important in this project is shown in the next slide, because what we also do for this case study is a second idea of producing these parts with a slightly different laser system configuration. That means we also are able to process this part with a so-called hull core strategy or skin core strategy. That means, yes, in this case we use a 1 kilowatt laser source, but only to produce the core of a part. That means what we do is we always expose the outer surface and the thin structures of a part still with a 400 watt laser source. As I explained before, that we need that small spot size to keep the resolution. But the internal core of a part we process with 1 kilowatt with a top hat profile. So the energy density and the intensity itself in the beam spot is always the same in comparison to a Gaussian profile. And we only expose the core after every second or third layer. So if you remember some slides before when I explained the physical model, we increased the layer thickness virtually because we just exposed the core after the second or third layer. This is one thing. We use higher laser power. We defocus the beam for the bulky areas. Usually for these parts, because they are quite small, you have seen that, it's possibly not that interesting. So that was the reason we also in this movie we processed the parts with twin laser, 2 times 400 watts. But we made already some tests, because the big advantage of this skin core strategy is that we can achieve quasi-single crystalline microstructure in the core. And that's very important for turbine parts when it comes to centrifugal forces. So this is something we are still working on. It's still a scientific thing in development, and it's not possible in all materials. So it's only possible in stainless steel, Inconel, Hastelloy X, and cobalt chromium. But you see that this looks really different in comparison to the outer surface of the part, which usually has a quite chaotic microstructure. So this was one of the aspects of this business, this case study, which we got out of it. We already made some trials with this laser configuration before that case study, but here we could really use it. And so we made also these tests with the hull core and hull skin core strategy. And we found also out, what was very important, that we get good reproducibility. So it was possible over the different test cubes and the different layer thicknesses we produced with to get to achieve almost always the same kind of density. And what was important, as I said before, it must be more than 99.0. This was possible. So, as I said, it's still a running project. That means this is just one part of the result. The things are going on at the moment. We are talking about automation. We are talking about quality control. We have already some quality control systems in our machine. But for this project, we have some other things and other ideas for the future. So there are still things going on, and this is a running project, but I think it gives you already a quite good impression about what is also possible with this technology and this hybrid manufacturing, how we call it, when we repair something or build something on an existing prefabricated part or something like that. This is also one opportunity and one application of this technology. Okay, how can we now transport this to a high batch production, which will be the result of this case study? So one day this should end up in a serial production. And this is possible with, I want to show you with the next movie, because this is then the movie about our SLM 500, how it works with producing with 4 lasers simultaneous material. So enjoy, please. Three minutes? That's enough. We are producing here 2 gear housings for a race car in aluminum. 2 huge gear houses in a time of around about 70 to 80 hours. This is the way the material is sieved after the process. So the red material is the overgrain material, which goes to a different bottle, and the rest is transported back to the main tank for using it for the next process. So a complete closed loop powder cycle we have in this machine. So that's the reason, and I said it's dedicated for using that for serial production, because the powder is always in a closed loop powder cycle under process gas. So that usually the operator never has to touch the machine during the operation. And the machine has also a pellet system or changing system. It's not similar to a CNC machine, but it is a kind of pellet system where you can change the build cylinders after the process and put an empty build cylinder already inside, so that the downtime of the process is really reduced to 20 minutes, half an hour, whatever. So, and when we just have a look to these gear houses we produce here, then usually these are for a race car. It makes no sense to cast that because the tooling is quite expensive, and that's the reason we process this for the customer in additive manufacturing. Yeah, that means, last but not least, when we have a look to the productivity of our machine systems, and if you compare a single 400-watt laser system to a quad 4 times 400-watt laser system in an SLM 500, that we can increase the build rate in cubic centimeters per hour by 235% as an average. And this is really the fastest build speed at the moment in the market. And this is our idea, how we would like to push this technology for serial production. We already did it. We have several customers already using this technology. One of our customers has already 8 machines for serial production. And we think about more automation for the future. So just as an outlook for the future.